Hi, and welcome to this short content bite, which introduces the third law of thermodynamics and perhaps will surprise you when I go a little bit off topic at the end. Unlike the first three laws, the zeroth, which introduced temperature, the first, internal energy, and the second, entropy, the third law is perhaps not a real law in the same spirit, as it doesn't introduce a new thermodynamic concept. Instead, it extends our understanding of entropy, and I've already alluded to it elsewhere. Just like the other laws, there are various statements of this law, from statements like the entropy of all perfectly crystalline substances is 0 at 0 Kelvin, but the net result is usually that we can't cool to absolute zero. Well, we could use the physics of the process and talk about fluctuation dissipation theorem. This basically says that as the temperature of a material falls, the occupation of the energy levels tends to favour lower energy levels, and the spread of the occupied energy levels falls. So when only a few energy levels are populated, the heat capacity, the amount of energy required to raise the temperature of a system, falls, and consequently small amounts of energy lead to large increases of temperature. Physicists have cooled Bose-Einstein condensates to temperatures as low as 0.00000000001 Kelvin by making use of the spin of electrons in the system and aligning the spin of these electrons with external magnetic fields at constant temperature. This alignment of spin reduces the entropy of the system. When the magnet is turned off, the spin relaxes, but there is no change in the entropy of the sample, and so to balance this, the temperature must fall. This process is repeated again and again, but we can never reach zero this way, just iterate ever closer. An interesting aside, whilst it is impossible to reach absolute zero, if I can invert the population of energy levels, then I have a negative temperature. I have to. It is the only way I can still fulfill the Boltzmann distribution. Okay, why is this relevant? Well, lasers rely on population inversions. They only work by having more molecules in an excited state than in a ground state. And if we use our definition of temperature from our zeroth law, lasers, at least when they are working, have negative temperatures. But this just shows how odd our new molecular understanding of thermodynamics is. There are some unusual consequences of thermodynamics, from having a temperature which we rely on to define our scales that we can never reach, to our definitions leading to something that just doesn't make sense. Thermodynamics was set up over 200 years ago as a way of predicting steam engines, and now, with our understanding of these laws, people are reaching temperatures just 1/1,000,000th of a Kelvin above zero. I hope this has been interesting. If you have any questions, please do not hesitate to ask.